Hi, this is Professor Stugard, and in this video we are going to do some linear regression on the Boston housing data set. So I've already opened up my Jupyter Notebook home screen, and I'm going to create a new Python notebook. So first of all, let's title this. So I'm going to call this Boston housing linear regression Stugard, because that's my name. And so in this one, we are going to take a look at the data set Boston Housing, which is a default data set in the sklearn, so that we're going to be able to kind of manipulate it and hopefully be able to, well, model the pattern in the housing prices based upon whatever variables are going to be the most predictive, which ones have the best correlation. So we're going to have to do some EDA on that data set first. But before we do that, I want to make this look like a professional report. So what I'm going to do is in my first code cell here, you see how I have the option code? I'm going to change that to Markdown so that I can now actually type and make this look kind of nice. So there's lots of different ways that we can edit Markdown. What I'm going to do first is kind of create a heading. So we do that with different number of pound signs. So 1 is the biggest, then 2 is a little bit smaller, 3 is a little bit smaller, 3 is a little bit smaller still. So again, this is going to be my Boston housing analysis using linear regression. And if I run that code now, right, it just types that nice one here. And if I ever want to edit this, even though it doesn't look like it's a cell, if I double click, I can go back and edit it, and I need to run it again to make it appear. So I'm going to do one more Markdown because I also want to include prepared by, and I'll put my name. And that's probably a good idea to include a date as well. Let's see, a date. But yeah, we're going to make this kind of general. So I'm just going to say just prepared by Nick Stugard. So again, include your name, include a title here, use that Markdown. There's other things we can do too. We can do bold and lists and include code snippets and a bunch of other cool stuff with using Markdown. But let's just jump in and take a look at this data set. Now, of course, first I need to import my usual packages. So of course, pandas as PD, import numpy as np, import matplotlib.pyplot as plt, and we'll start in the beginning. We'll do that's all right. We don't have to do it inline. So again, we have our packages, and actually let's comment each of these two. So let's import our libraries and data set. So let's actually do that in this code chunk too. So I'm going to go down, and then from sklearn, again, that's the package we're pulling this data set. So sklearn.datasets, we'll just pull what we need. Data sets. We're going to import the load Boston. And then from there, I can then pull my Boston data. So I got to create an identifier, create an object in my environment. I'm going to call it Boston data because again, this is just going to be the raw data. And I'm going to basically take that from my load Boston function that I just imported. So again, the load Boston is a function, so make sure you put the parentheses at the end. We'll run our code here, and we should have our data. But if I look at Boston underscore data, and I just want to take a look, I see, all right, data, it's stored in an array. We have all these values. And so again, we have our data here, then we have our target. So we can see that our target is separated. We have the feature names stored in an array so we can see what our feature names are. But again, it's kind of ugly here. We also see that we have this DESCR. So let's do a few things here instead. So I want to print, and let's start from our Boston underscore data. And if I do dot feature names, feature underscore names, which again, I'm taking that from here, right? I can see feature names is obviously a thing. I can run that, and I see that my features are, well, CRIM, ZN, INDUS, age, RM. Okay, so we got a bunch of different things going on here. So again, it's kind of hard to tell what my features actually are. So what's really nice is that if I do capital DESCR, which again, that was part of just, if you're looking at the Boston data, this is going to describe my data set. And again, this is really nice because it kind of comes with that default sklearn, because, well, it's to help us learn how to do machine learning. So the Boston data set, all right, so we really have Boston house prices, our data set characteristics. There are a number, 506 instances, so 506 observations, data points for us to use, attributes. So we have 13 numerical and categorical predictive attributes here. Median value, which is attribute 14, is usually the target. So again, that kind of makes sense. I'm trying to predict the price of the housing, so the median value is going to be my target. Now we have all those features. So CRIM, that is our per capita crime rate by town. ZN would be our how the land is zoned. INDUS, so now we're looking at non-retail businesses in acres per town. CHAS, the Charles River dummy variable, which is stored numerically, but it looks like 1 if we're by the river, 0 otherwise. So again, the riverfront property is probably a bit more expensive. NOx, nitrous oxide concentration in parts per million. RM, our average number of rooms. Age, the proportion of the age. DIS, weighted distances to the 5 major Boston employment centers. RAD, accessibility to the radial highways. TAX would be property tax rate. PT ratio, pupil teacher ratio. B, proportion of blacks by town. Okay. LSTAT, the percentage of lower status of population, so I'm assuming that's socioeconomical. And then, of course, that last one, MEDV, our median value, in terms of the hundreds of thousands. It says missing attribute values, none. I don't know if I believe that, so I'm going to double check it. We see who created it, where this data set is housed, where it was taken from, Carnegie Mellon. And again, we can see that it was used as a regression diagnostic. So that's probably a good sign for us doing regression here as well. Again, it's been used in many machine learning papers that address regression problems. So, yeah, we're pretty much doing exactly what this data set is designed for, which is why it's included in the sklearn. So I'm going to leave that up because we might want to refer back to that later as we progress through. It'll be nice to still have that there. I can also see if I print my Boston underscore data dot the target. Let's see what our target looks like. And good. So we have a bunch of numerical values. And again, we see that the median value is our target, and that's in terms of thousands of dollars. So we have different numbers in terms of the thousands of dollars here, which is useful. But again, I don't necessarily want to see this whole mess. So what I'm going to do here, though, is, again, I have my data set. This is all the raw data. What I want to do is actually turn this into a data frame. Because data frames are much easier to work with, much easier to visualize. And again, it's just kind of the preferred way to store data when doing data science type analysis. So I got to create an object here. Like I said, I'll get rid of that. So I'm going to call this the Boston underscore DF for data frame. So again, the underscore data is my raw data. Data frame is, again, going to be stored in that nice data frame format. So to create a data frame, it's from the pandas data, or the pandas library. So we got to start with the PD dot and then data frame. Capitalize the D in data and the F in frame. So again, I'm going to create that data frame. That is my function. So inside the parentheses, the arguments I want to define here is, first of all, well, what am I actually using here? And so we're using the Boston underscore data dot the data itself, comma, and then my columns, I want to include my column names, and my columns are going to be equal to my Boston underscore data dot, and those are those feature names that we looked up earlier. So feature underscore names. And then just to make sure that my code worked properly, because again, here I'll run it, nothing happens. I don't know if it worked or not. I'm going to then do my Boston underscore df dot, use the head function just to see the top, the first 5 rows here. Make sure it looks good. And so it does. Looks like, again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have our 13 features, and we don't see our target here because again our target's going to be separate. So let's store our target then, because these are again just going to be our features. So for our target, let's see, I'm going to take my Boston underscore data frame. I want to create a kind of a new column here, and it's going to be called the MEDV, that median value. And that is going to be equal to my Boston underscore data dot the target that we looked at. And again, we won't be able to see anything if I just run this, so I'm going to do the same thing that I just did. Take my Boston underscore data frame dot head just to see the top 5 rows, make sure it worked. And if I run my code now, good. Now my last column is that median value. So again, by default, the data is just my features. And so I'm going to have to add my target in because it was stored separately. Because again, I want this all as a data frame because it's much, much easier to manipulate a data frame using what we know already about data science. So the next step is to clean this data up, do some EDA. So again, we have all of our data loaded. Now it's time to do some data cleaning. So again, the nice part is you can go back to Markdown and I'll say, all right, 1, 2, 3, because again, we want a little bit smaller. This is where we're going to do our, we'll do our EDA. We'll do some exploratory data analysis. Run that code. Again, that'll give us a nice markdown and give us a nice break. And again, it'll make my my whole report just look better. And I'll be able to find different parts of it. Because again, we're trying to put everything together here. The EDA, the graphing, the regression, the modeling, all of it together. So first of all, I can take my Boston underscore df, now that I've stored as a data frame. I can just run the info function. So Boston underscore df dot info. I run my code, and we see, all right, so I have 506 entries from 0 to 505, and it looks like my non-null, so 506 in each of these, and it looks like every single piece of data is stored as a floating decimal point, which is good. That's what we want. A good thing to check for too, again, we see we have, it looks like 506 values, so everything's filled in. Always a good idea to check as well if there are any missing data. So I can do that by again using the print function, and I want to print my Boston underscore df, right? So I'm going to use the print function. What am I going to print? Well, I'm going to take my Boston data frame, and then I'm going to run that is null function. And then what I actually want to do is, again, it's going to run is null, and then that's going to return the Boolean, either true or false, which the computer recognizes as a 1 or a 0. And so what I actually want to do, instead of getting a huge big mess, because, well, we'll run it first and see our mess. Data frame has no attribute is null. What did I do there? Data frame is null. Well, I wanted to do a sum anyway. Let's see if that works. Sum up my null data. Why don't I have... Why don't I have my function is null? Oh, because you have to spell it right. Oh my goodness. Is null. Wow. Well, that's what this is really like, right? Gonna make lots of mistakes. Double check your spelling, right? Only do exactly what you tell it to do, not what you want it to do. So if I run is null in the sum, all zero. So there's no missing data, which is really nice. So I can move on and I can actually start figuring out what are going to be the best variables to use here to actually do our modeling. I don't necessarily want to use all 13 different features. I want to choose the best ones. So we have no missing data. So now I can do markdown. 1, 2, 3. So now this is going to be where I select the features to do my model. So model select, or my feature selection, or select some features. So what I want to do is, of course, find my correlation coefficients. So that's how I figure out which ones have the best patterns to try to draw from. So we're going to find correlation coefficients. And I can comment this. I should probably be commenting my code a little bit more anyway. So I'm going to call this the CORR. Again, I'm going to create an object in my environment to store my correlation coefficients. And then again, I'm taking my Boston underscore DF for my Boston data frame. Just ready the correlation coefficient function. And then I want to actually print it as well. I want to see it after I store it, right? Because again, if I don't include the print function, it just happens in the background. So we print. And good, I got this whole big table with all these decimal places. Like I said, I probably don't need that many decimal places, so I'm going to round it. And I usually choose 2 as my default round. I just think it looks a little bit nicer. So again, we see we do have, like I said, 14 different variables here, our 13 features and our 1 target. So it does take up quite a bit of space. Now again, I can go through and look for the best ones here. I always like to do a heat map, so let's make a heat map as well. To make our heat map, we need the Seaborn package. So because now I decided that I need it, I'm going to import it at this step. And again, I probably knew I was going to use it anyway. So if you wanted to import it at the beginning, you could. And again, our typical way we import Seaborn is as SNS. And then now my SNS.heatmap. I'm going to take my data is that correlation thing that I just, my correlation coefficients here that I just created, right? My object correlation, that's my data. I do want to include the annotation, so annotate equals true. Remember with true in the Python programming language, you just capitalize just the T. Otherwise it doesn't recognize it. And with my correlation coefficients, I know it goes between -1 and 1, so I do want to set that by default. So my V min equals negative equals -1. My V max equals +1. I'm going to center my heat map around the variable 0, right? That should have no color whatsoever if it's 0. And then I like to switch up my color map. And again, I like the red and blue, which is VLAG. And then I'm going to then do my plt.show to see my graph. So hopefully I did everything right here. We run my code. What did I do wrong? Right, it was in there. Draw the heat map. The arguments. Has no property V. Oh, ha! Has no property VAMX because I spelled VMAX wrong. So, double check that. Run my code. Name PLT is not defined. PLT.show. Huh. Oh well. I don't know why I'm getting that error message and it showed the graph, but that's all right. I can remove that. Okay, so this is kind of a mess. This is way too cluttered for me. So I'm actually going to go back here. We can see those numbers are right on top of each other because, like I said, there's a lot of variables here to look at. I'm going to actually round it to just 1. I think that'll be all right. We'll round it to 1, And then we can take another look at the heat map. We'll rerun that code. This is a little bit better to look at now. All right, so my target is the MEDV. So I can either look at the row here or the column here, and I want to find which are going to have the best possible correlations to look at. All right, so it looks like RM, that's a 0.7, and LStat as negative 0.7. Those are the darkest colors, so one has a positive correlation, and again, the red is a positive correlation, and then the blue is a negative correlation. We can check to see if there's, we can, like I said, we can see pretty easily here that those have got to be the top two. So we're going to pick those as our top two. We could go through and actually check numerically as well. Again, I like the heat map. I love visualizations. We could also check, we could do, we want to use the absolute value function because, again, we have negatives and positives. And I could do absolute value function, look at my correlation, MDEV. Actually, let's go back. Let's not round this at all. Let's go back and get the whole values just in case. So I want the absolute value of the values in my variable, in my column here, MEDV. And I want to see which are the ones that are strictly greater than 0.5. What's greater than a half? And we run through the Boolean. Yeah, it looks like RM is true, so that one's true. The PT ratio is true, LStat, and then MEDV, which again, remember it's asking it what's the correlation to itself, which is always a 1-to correlation, so we're going to expect that to be 1. But yeah, it looks like there's 3 of them that are there, which are pretty, that's actually pretty useful. What I can do is I can actually, again, if I didn't want to use the heat map, I can choose what are the top 3 features, and I can print their correlation values as well by just manipulating the print function. So let's try that. I want to print, and I'm going to start with my Boston underscore data frame. I'm going to run my correlation function. Now again, I could just start with the correlation function, but again, I rounded it, but this is if you didn't want to create the heat map and everything. So again, I can run that function inside my print function. It'll still work. Like I said, I want to find the absolute value. So again, I'm basically applying function to function to function, kind of chaining them together. So create the correlation coefficients, take their absolute values to find which has the biggest absolute value, so we don't have to worry about negatives and positives. And then I'm just going to choose the n largest. That means choose the ones that are the biggest. And first I got to define how many I want. Now again, I know that I'm looking at the median value. The median value is always going to be correlated with itself 1-to-1, right? You know, we look at the heat map here, that's of course 1-to-1. So that's going to be included by default, which means I actually want 3, because I'm going to choose the top 2 features, but I need to choose 3 because it's going to include MEDV. And again, I want those from that column, MEDV. So I'll put that in my single quotes or double quotes. So I only want from that particular column. And then, let's see, is that going to run? Yeah, so that lists the top 3. So median value, LStat, and RM, and it lists all of them. I don't necessarily want all of them. So what I'm going to do is do one last one, dot index here, and then it'll just print the index. I just want the index. What are the top 3? MDEV, LStat, and RM. So that's really good. So again, I can go through it this way. I can go through it this way. If I want, I can include another line. I can print, again, from my Boston underscore DF dot correlation coefficient dot absolute value dot, dot n largest. And again, I'm going to choose the top 3 from the MEDV, and spell it right, MEDV. But what I'm going to include at the end, instead of .index, instead of just seeing what the names are, I want to see the actual values. So I can say, what are the values here? And again, include all the rows, but I only want from column 13, which is my 14th variable, but again, it's that Python indexing where we start counting at 0. So if I run this code beneath, we see, again, MEDV, that'll be the first value, so it's a 1-to-1 correlation. We knew that. LSTAT has a 0.737. That's pretty good, especially for a data set that we said had over 500 values. A correlation coefficient that high, that's pretty good. And RM. So these clearly are our top features. So here, we'll make a markdown to actually describe this. We don't need a heading. We'll see the top predictive variables are. And again, if you want to actually type in like code chunks, which I think kind of looks nice, you use the tick mark, which is the one like next to the tilde, like the one next to the one on your keyboard. So LSTAT, LSTAT, and RM, which are, well, yeah, we should probably figure out what variables are the most predictive here. So if I go back to my description, again, LSTAT, percentage of lower status of the population, and RM is your rooms. So, which are the percentage of lower, wait, what did they call it? Lower, LSTAT, percentage of lower status. Percentage of lower status and number of rooms respectively. Hopefully I spelled that right. There's no spell check here. All right, so again, the top predictive variables are LSTAT and RM, which are the percentage of lower status and number of rooms respectively. So look at those are the top two predictors. The rooms make sense. Again, that makes a lot of sense. And then the percentage of lower status, I guess we're talking about the neighborhood here, right? Location, location, location. And I guess that's true, right? It's real estate. So the best predictor is location. The second best predictor is the number of rooms. And then again, those are kind of clearly the biggest ones here. We can take a few other looks. So again, when I round it to one variable, it looks like the tax rate also wouldn't be a bad predictor. But again, that must have gotten rounded up. So is the indus. So again, we got all that kind of good stuff. So let's actually do, let's make some plots. Let's make sure we know that this pattern exists. Let's actually visualize the pattern. So yeah, now I'll include, let's see. Yeah, the top predictors. Yeah, so let's do our visualization. So I'm going to make sure they're in line. I'm going to do that percentage notation. So percent mat plot lib in line. Make sure it's all in line. Give myself some spaces. So PLT, and again, I'm just going to do a scatter plot here. So scatter, and from my Boston underscore data frame, I'm going to choose again my kind of my X and my Y coordinates. So we'll start with the LSTAT because that was the most popular one. Oops, almost forgot. You got to put the column names in quotes because we got to search for that column name, which is again technically a name. So put that in quotes. So there's my X variable, and then Boston underscore data frame square bracket, and then I want the median value. So again, I just want to plot my my feature and my target together, and I can change some options here too. So I can change my marker, and let's do the O marker. I kind of like that one. And then PLT, we definitely need to label. So my X label is LSTAT. PLT.Y label is, of course, my median value. So if we run the code, line magic. Why isn't the line magic found? Oh, well. I'm not going to mess with that. I'll just do my PLT.show. So we'll run my code. PLT is not, that came up again. So I must have made a mistake up here. Oh my goodness. That was really, really silly of me. I imported it as PLY. No wonder I couldn't find it. That should be PLT. That should make a difference because the Boston data still gets loaded as Boston data, but we're not overwriting anything. So That was silly of me. But again, this is what coding really is. You know, finding your mistakes. So run my code. That must have been why when I made my heat map, the plt.show didn't work. plt.show. Probably should have recognized that. Yep, now get rid of that one. That's, oh well. I want it all to look nice. I'm going to go back to rounding to 1 and then do my heat map. That looks so much nicer. Okay. All right, let's try this again. So now, here's my scatter plot. And so we definitely see that there is definitely a pattern to this data. There's definitely that negative correlation, that negative association, meaning that as the percentage of the lower status goes up, the price goes down. So as lower status goes up, price comes down. We have that negative association. We do see this weird thing where it looks like it caps out at 50, and we have a lot of values here at 50. So that's weird. Why is it capped out at 50? Okay, not the biggest deal. Let's see if that happens with the other one. So the really nice part is I'm going to reuse this code. So I'm just going to copy and paste it. And all I need to change now is my lstat to rm for room. So I want the rooms now. Room. Run my code. Perfect. And we see the number of rooms. And again, we have that same, we have a pattern here. It's definitely increasing. We have some outliers over here where we have something with less than 4 bedrooms, obviously higher than we would expect. And we see this weird cap at 50 again. So clearly this data frame has some issues. It looks like 50 is the highest value that appears for my target, which again, not every data set's perfect. In fact, most aren't perfect. So that's kind of part of the territory. So again, clearly we're capped there, which is kind of an issue. We definitely see there's a pattern, even with our outliers. There's definitely a pattern here to this data. And that's okay, right? Data sets aren't perfect. Oh man, that was silly of me. I just realized I didn't include the parentheses. No wonder I have that description there. Make it a little bit nicer. Okay, kind of clean it up, make it look professional. Type the right thing here. Shift. There we go. Okay. So yeah, we definitely have this pattern. These are our 2 most predictive variables. We definitely see that. We see that the data is not perfect. But that's okay. That happens. What I want to do now, though, again, I want to use these 2 different variables to predict it, which means I have my 2 features and my 1 target. So what I'm going to do now is I'm actually going to create a 3D scatter plot of this. So when we do 3D scatter plots, we have X, Y, and Z. Z is our up and down, or the height here, and that is always going to be our target. That's going to be our dependent variable, which in this case, again, our target, our dependent variable, our response variable is the price, the median value, and then our features, our independent variables, those are going to be the lstat and the rm for rooms. Now, to do a 3D graph, I am going to have to import something else. So from the mpl underscore toolkits dot mplot3d. So mplot3d, good. I spelled everything right. So I'm going to pull from the matplot library toolkits. I want to pull the 3D part, and I want to import the axis 3D. So we capitalize the, oh my goodness, got to spell things right. I capitalize the A in axis, and this is going to let me plot things in 3D. Let's give myself some space. So I need to create an instance for my graph that I can kind of pull and use from later. So instead of really being able to pipe like we might in, say, R, we create these instances, we create these objects, and then just kind of call them back in a second. So plt.figure is my function that I want to use here. And that'll create my figure. What I'm going to do too, because I know this is going to be a professional one, I'm going to just find the size. So fig size, fig size. The size is my figure. And this is going to have two different inputs. So again, I'm going to start with 1515 because I kind of know what I'm doing. We'll play around with these and see what they actually look like in practice. And then AX, again, I got to create a new instance, a new object, AX. And so that's going to take my figure that I just defined. I need to add underscore a subplot. And then here, 111, and do a projection that is equal to 3D, which the D is lowercase here. So again, I want to add my subplot with my new object called AX, which is going to create a projection. The 111 is design size. So what I need to do now, so now that again creates my object. I have a 3D projected plot that I'm creating, and from AX I'm going to create a scatter plot because again I want it to be in 3 dimensions. So my scatter plot, so I want to define my X and my Y first, which are my two features, and then my last one, my Z, is going to be my target. So from the Boston underscore DF, I'll choose LStat. Then my next argument from the Boston underscore data frame be RM. So again, right, square brackets, once we use the data frame, that tells us to call something inside the data frame. What am I calling? I put it in quotes because we have to look for that character name. And then the last one, DF, or no, Boston underscore DF. My third one is the MDV. Oops, got to put that in quotes, two single quotes, MDV. Good. Again, I'm going to add other options as well. C is a default for color, so let's say I wanted to color it all red. I want to do my 3D scatter plot in red. I can define that as well. And then, like I said, I want to label this. So AX, because again, that's what I'm looking at. And now I'll use the set underscore X label function. A little bit different, but same idea. So my first variable was LStat, then AX dot set underscore Y label, and that'll be my room. Good. Then the AX dot set underscore, and then my Z label, my Z axis, and that'll be MEDV, spelled that right. And then the last thing, the PLT dot show as a function. And let's see here. Figure size 15, a positional argument follows the keyword argument. What did I do here? Why did this decide not to work? Positional argument. Oh, maybe I can't. Well, let's leave that blank for now. All right, well, here's our pattern. I wonder why my figure size didn't work. Oh, I think I know what it was. Yeah, so here it is by default, fig size. Yeah. Yeah, fig size needs to be its own function. And I'm going to define it as 15 comma 15. Did that work? Fig size is not defined. Oh, yeah, equals, and store it as an ordered pair. Ah, there we go. Now it looks a little bit bigger. So 15, 15, we can see the scatter plot. We definitely see a pattern here in 3 dimensions, right? We still have our median values are up and down. LStat, RM, we can see that in the LStat direction, it's definitely decreasing. In the room, as it increases, that also increases. So that's kind of cool. We get to see this whole thing in 3D. So the fig size, again, I can adjust this. If I change the first value to a 5, we see what happens. Oh, that shrinks my XY. And if I change the second one to a 5, it shrinks the up and down. So again, we can play around with it to make it look the best for that particular graph, that whatever I'm using. But yeah, that looks good. And again, I can still see my pattern. And again, it's kind of cool to see these things in 3 dimensions. All right. So this was all part of my EDA. So now let's do a markdown, and we will now 1, 2, 3. Now 1, 2. Now we will train the model. All right. So what we're gonna have to do is, of course, well, split my data into testing and training data. So we'll start with that now. All right. So let's see. How do I want to start this? All right. We're gonna pull first. First, we're gonna pull just those features that we want. So I'm going to say my features X. Actually, I guess I should use capital X because, again, we're pulling multiple features, so it's going to be like a matrix. That will be, so again, I got to take from my, let's see. Yeah, PD data frame. I want to make this into a data frame. I definitely do. We're going to do the NP. This is a NumPy one for manipulating data frames. And C underscore. And again, we're going to list the columns. Basically, this is going to give us, store what we actually want as our features. We're going to list the columns that we actually want here. So from the Boston underscore data frame, I'm going to pull the LStat as my first one. So that's the first one outside of that quote. Okay, good. Again, checking to make sure that all the brackets match up. So I'm still creating my column of the ones I'm going to pull from. So LStat is the first one, and then from the Boston data frame, bracket RM is the second one. And like I said, when I create my new data frame, I'm going to include the name for my columns. So columns equal, and again, as a vector, LStat in quotes, and then RM in quotes. All right. And then let's just print X to make sure. Oops. All right, where's my error? Columns equals, that isn't the right syntax. Columns equals. All right, well, let me see if I messed up any of the other code. So I'll cut that. Everything should match up. Good, that worked. If I look at X, yeah. Okay, that all worked. Why didn't naming my columns work? So yeah, we have all of our rows. Again, this data frame is just the 2 variables, which is nice. So the data frame, oh, I know what I did. I need to be outside that last bracket, I think. Columns equals, and then my vector, LStat, comma, RM. Let's see if that works. No error messages there. And so if I print x.head, that looks exactly like what we want it to look like. LStat and RM. So we have our variables. Perfect. So again, what I did here, I comment my code, define the features. Now we have to, well, define the target. So same idea, lowercase y now. And from here, the nice part is, again, we know it's from the Boston data frame. Boston data frame. I don't have to actually make it into a data frame. This is much, much easier because it's just one column. It just needs to be the vector. MEDV. Done. And a good idea to check it, right? So we'll print y.head. First 5 values. Good. All right. Again, we see the vector is a floating type, so that's good. All decimals. Everything seems to be stored well, so we're good. So next up, we need to create the training and test data. We need to create those two. So I need to import some stuff from sklearn. From sklearn, yeah, I'll just take the part that I need. So from sklearn, we'll do our model underscore selection, and we're going to import from the model selection our train underscore test underscore split. So that'll import the function that we need. And then the nice part is, again, I can define everything here. My test data, my training data, I can split it in terms of the targets and the features, all in the same line. So capital X underscore train, then capital X underscore test. Again, we take our features first. It'll split up the training and the testing data that way. Then Y underscore train, comma, lowercase y. Y underscore train, comma, Y underscore test. So I'm creating those 4 different objects, and I'm training my testing data for everything. I'm going to figure that out from running that function I just imported, my test, train underscore test underscore split function. And how do I want to do this? Well, I'm taking it from my capital X, comma, my lowercase y. By default, the test size is set, but it's not a bad idea to define that as well. So test size, again, I like to always do my 25-75 split. And then to make sure that yours actually is going to match mine, we should set our random number seed. So random, the way we do that in Python, we set the random state, and let's choose, I don't know, 5. Doesn't matter. But we'll run our code. No module called sklearn model selection. Oh, because I spelled it wrong. Selection has an extra E. Oh, spelling issues, right? Good. So that looks like it worked. I don't necessarily want to look at the heads, but I do want to just make sure that it should be the right size. So I'm going to print x underscore train dot shape. That'll tell me the dimensions here. Good. X train shape. And then we'll also print the y train dot shape. Make sure that they're the same size. Good. So the X train shape, 379 observations with 2 variables. But of course my y, my target, only has 379. Let's look at what the test data has, what we're going to test against later. So again, basically copy and paste that same code. Just change the word train to the word test. We run that. Good. And my testing data has 127 points. So again, we have more data in my training. Hopefully it's 75%. Again, that's why I set my test size. I'll double check really quick. What's 127 divided by 127 plus 379. Oops. Run the code. Yeah, 25%. Perfect. All right, so get rid of that. Now it's time to actually create our model. So now we got to actually load our model. So this is where we actually create the model. Let's include that. So again, we're going to pull from sklearn, and again, we do this kind of one step at a time. And I want to create a linear model. So from sklearn.linear underscore model, we're going to import linear regression, which that is more the camel case. So capital L for linear, and capital regression. Let's make sure I spell that right. Capital R for regression. So that'll import the linear regression model or the linear regression function that I want to create my model. And so my model equals, so this is going to be my model. My model is going to be my linear regression function. Which again, we create that instance so that I can kind of adjust my model on the fly. And my model, which is now defined, and I create my instance, my object for linear regression, I need to fit it to x, capital X underscore train, comma, y underscore train. So again, I create my linear regression model and I need to fit it to my data. I run, and my output is linear regression, which means that, well, it actually worked here. So we need to see how well this works. A couple ways we could probably do this. I'm going to create a new object in this case. So my price underscore predictions is going to be equal to what my model, right? My model function is why I created that instance. What it predicts using my X testing data. So we're going to basically see how well it works. My predictions, what is it going to predict for my testing variables? Because again, create my model. My model's already done. That's like the easy part, right? It was literally like 3 lines of code, created my entire model. Now I want to see how my model actually works against my testing data. So we create my object for predictions. So again, this is basically, I'll comment this. This is where I'm going to evaluate the model. How well does it work on my test data? And so then I'm going to print, let's actually see how this works, my R squared value. So again, that is my correlation coefficient that we usually use, R squared. R squared. And so I'm going to include a little bit of code that we haven't really used yet with the print function. And there's actually other ways to do this too. But inside my print function, again, I want it to print out how well it did, how well it made my predictions. So my R squared value, the percent sign dot 4, we'll go to 4 decimal places, F. That's the end of my quote here. And then that percent symbol, what I actually wanted to include there is going to be, add a space, my model dot, and I'm going to score it. And I'm going to score how well it does with the X test. Oops, X. I want to score it, my capital X underscore test, compared to my Y underscore test. So those are both separated with a comma here. All right, so let's see. So my R squared value, 0.6294. So again, that's basically my R squared correlation coefficient. So that's not too bad. Again, for a data set with 127 values, that's okay. Not perfect. Again, we know our data set wasn't perfect, but that's actually still a decent predictor. We would definitely call this a successful model to use here. So let's go a little bit deeper into how well this worked. Let's look at the mean squared error for this model. So from sklearn .metrics, which again, this is the part that lets us actually evaluate how well our model worked. And there's lots of different metrics. We can do the accuracy of the model, which would be more of a classification type metric. For our linear regression, we want to use our mean squared error, right? That's how we determine how well our linear model works, right? Takes the residue, right? The error, we square it, sum it, figure out how well it works. And so that is the function mean underscore squared underscore error function. So from sklearn metrics, I want to import the mean squared error function. All right, and then we'll say that's MES because that's way easier to use. So let's abbreviate that as MES, which is going to be equal to my mean squared error function. Let's actually plug in our values here too. So y underscore test. So my test values, right? So again, this is actually probably, I'm like skipping steps here. We evaluated the model. This price predict one. This is what I predicted. So the y test, this is the actual. So how did the actual compare to what the model tested? The predicted price for the test. So that's going to be my price predict variable that I created already. So price underscore PRED. Yeah, so we'll find the mean squared error is those two, and let's print what my MSE is. Mean, oh my goodness, I gotta spell things right. Mean squared error. So my mean squared error is 30.59. So what does that actually mean? Well, let's visualize the error. So now we'll visualize the error and actually see how well we did. So we'll do a scatter plot. So plt.scatter, and then I'm going to use my y test. Basically what I just set up, my y test and my price predictions. So the actual value is going to be along my horizontal. The predicted price is going to be on my vertical. So what we would really want in a perfect world, those are going to be on a perfect line. A perfect one-to-one correspondence, going to perfectly have the test value and the prediction. We know it's not going to be perfect because our correlation coefficient wasn't 1. Our mean squared error was 30.6. So we know it's not going to be perfect, but this way we can visualize and see how well we did, and we can also see where did our model make some errors. Because again, perfect world, it'll be a perfect correlation, a straight line. We know it's not going to be that, but we can visualize how far off we are, and that's what the scatter plot's going to do. Again, as always, let's label it. So plt.myxLabel. Like I said, this is going to be my y testing data, so this is going to be my actual price. And my plt.y label, that is going to be my predicted price. And then let's put a title. So plt.title, and we can see that this is going to be the actual price versus the predicted price. Actually, since we're looking at more, actual prices versus predicted prices. And then plt.show. And here we go. We can see that there are a few places that we're off for the most part. Again, we have a really, really nice pattern here. But if you notice, this is kind of weird. My actual price goes up to 50, right? We know that it goes up to 50, but it was capped there. But we can see that, here we go with my test data. None of the predicted prices went above 40. And again, that is probably an error kind of baked into that data set, which again, we knew the data set wasn't perfect, but again, this is pretty good. This is pretty close to that vertical line, that one-to-one correspondence. So again, I'm fairly happy here. And this is all I really wanted, and this is actually going to wrap it up. So we have our model, and we see how well it works. Let's actually define our model. So let's go a few steps further here too, and actually figure out what is my actual linear model. What are the coefficients here that are going to work? So I'm going to print, first of all, my model that we created. I want the intercept. I'm going to add the underscore here. So again, model. Remember, model was my object that I created way back here with my linear regression model that I fit to my training data. So I'm going to print the intercept, and then I'm going to print my model dot coefficient. I know I spelled that wrong. Coefficient, and then my underscore. So take a look at those two. Oh, linear regression has no attribute coefficient because I spelt it wrong. No, I didn't spell it wrong. Doesn't it? I think they abbreviate it. Wait, let's try COEF. There we go. COEF. So we have my intercept and my coefficients. What I want to do now is download this. And again, I want to download this as a notebook so that it can be run. And we can download this as a couple different ways. And if I wanted to create a professional report that I was actually submitting to someone, again, I could export this as a PDF. And again, we'll see that it might take a second to create the PDF and load. Again, it's got to process that entire notebook together. So we'll give that a second to create it. But anyway, what I want you guys to do is to download it as a notebook. Make sure we download it as a notebook to submit for your assignment submission. All right. Well, I hope you're able to follow that. If not, please ask me questions if you got stuck anywhere. And as always, take care of yourselves.